Let's delve into conservation of energy. I already defined energy. I told you energy is the ability of doing work. We have two main types of energy: kinetic energy, which is always a half of mv squared, and the potential energy, which can be defined according to the system, like the gravitational potential energy, elastic potential energy. Potential energy is the energy saved in the system and potentially can do work. Okay, now let's define mechanical energy, a very important concept. Mechanical energy is a useful concept to have a sum for the whole kinetic and potential energy of the system. So let's define it as the sum of Ek and Ep. In fact, we ignore microscopic internal energy of a system. We have mechanical energy as a total macroscopic energy of the system. So this is the macroscopic kinetic energy and this is the macroscopic potential energy, ignoring any microscopic interactions. A ball of mass 2 kg is thrown at a speed of 10 meters per second from a height of 4 meters above the ground. Okay, the experiment is like this. I threw an object, a ball, from a height of 4 meters above the ground at a speed of 10 meters per second. This is the initial speed of the object. Find its initial mechanical energy. Okay, the mechanical energy is going to be the potential energy plus kinetic energy. About the kinetic energy, it's clear it's half of mv squared. But about the potential energy, I should first specify the ground state. It's very usual in physics to take the ground state at the minimum level that the object can reach. When I threw the object, the bottom line for the height will be the ground. So I take it here. So in potential energy, when I write mgh, the height is the altitude relative to the ground. It's 4 meters here. So let's plug in the values and we will get 413 joules. Here I have mass, the gravitational acceleration, height, a half of mv squared. Now let me continue with conservation of energy. When I say energy is conserved, I mean during a journey, the total energy of the system cannot change. Let's start with a very easy example. I release a ball from rest from top of a hill and the total mechanical energy is just gravitational potential energy, mgh. Let's say the ground state is here. During this journey, the object may lose part of its energy in the form of internal energy, and finally I may receive part of that in form of kinetic energy. This total mechanical energy at the beginning and the total mechanical energy at the end are not supposed to be equal. The reason, because of the frictional forces, we have some heat transfer, and part of the mechanical energy, unfortunately, is escaped from the system. But anyway, if we believe in conservation of energy, we believe that the total mechanical energy at the beginning will be equal to total mechanical energy at the end plus the internal energy escaped from the system. This is the meaning of conservation of energy. A very simplified case, idealized case, is the one in which mechanical energy is conserved. If we have the same process, ignoring any frictional forces, the total mechanical energy at the beginning and at the end are equal because there is no friction, so there is nothing to remove part of the mechanical energy in the form of internal energy. So we receive the total mechanical energy at the end equal to the total mechanical energy at the beginning. It's a very idealized case. So in in all problems in physics, we can use conservation of energy. But using conservation of mechanical energy is a very specified and idealized case in which the frictional forces are ignored. Conservation of mechanical energy. The mechanical energy of a system is constant provided that the system is isolated and is not subject to any frictional forces. In this case, if the total mechanical energy of the object during the journey is supposed to be constant, the changes of kinetic energy and potential energy can compensate each other and they always add up to a total mechanical energy of E. Let's say the total mechanical energy is 10 joules during the journey. So if the blue curve is the kinetic energy and the red one is the potential energy, You see everywhere they add up to 10. Means that, for example, here the kinetic energy plus the potential energy will be 10. Here the kinetic energy, the potential energy, and the kinetic energy will add up to 10. They compensate each other. The horizontal axis could be everything. Could be x, could be distance traveled, time, whatever. So in short, we can say we have two conservation types: energy conservation and mechanical energy conservation. If there is no frictional force, energy and mechanical energy are both conserved. You can use both of them in problem solving. But if frictional forces are not ignored, energy is conserved, but you cannot use mechanical energy conservation. An object is released from a height as shown, and it hits the spring and results in a compression on a spring to stop. Analyze the energy in this journey. Ignore any frictional forces. Okay, if I ignore frictional forces, I can use conservation of mechanical energy. Here, the object, let's say it's released from the height, so there is no initial speed, it's 0. Then it hits the spring, has no compression, still no compression, and then compresses the spring and stops. So here the final speed is also 0. Let's take the minimum height the object can get as the ground state. So it's the ground state. Here we don't suppose any gravitational potential energy. Now let's start analyzing the energy. At the point A, if it is at a height of h relative to the ground state, the mechanical energy is just gravitational potential energy, mgh. There is no elastic potential energy because it has not already involved in compressing the spring, and also as it has no speed, we have no kinetic energy, just mgh. When it hits the spring here, part of the energy now is in form of kinetic energy. So it has a half of mv squared. It's the speed of v is the speed of the object when it hits the spring. And part of that still is in the form of gravitational potential energy, mg times the altitude here. Let's say the altitude is x here. So mgx. Okay? Smaller than mgh, but still it's not 0. When it stops here, it's in ground state. There is no gravitational potential energy, but we have a half of kx squared, elastic potential energy. We don't have any speed, so no kinetic energy and no gravitational potential energy as the object is in ground state. If the initial value for the mechanical energy here is 10 joules, again here is 10, and again here is 10. It's the meaning of conservation of mechanical energy. Energy changes in pendulum. We have a pendulum here, and it's released from the right dead point. It's the dead point. Maximum height relative to the ground. You see when it's released, it will gain the maximum kinetic energy here, and then minimum kinetic energy, maximum potential energy, and so forth. There are 3 important points: the 2 dead points and the rest point. Rest point does not mean that here the bob is at rest. No, here the bob has its maximum velocity, but we say it's rest point because out of any speed, out of any mechanical energy, the bob will rest in vertical position here. This is why in physics we say it's rest point. Okay, let's say the maximum height of the bob relative to the ground state, here is the ground state, is h. Okay? As you see, potential energy and kinetic energy are continuously converting to each other, but they add up to E because we ignore frictional forces for the time being. In the first right dead point, the potential energy is mgh, and there is no kinetic energy. At the bottom point, the rest point, potential energy is 0, and it's in maximum speed, so kinetic energy is E. And here, potential energy is mgh again, and no kinetic energy. If we ignore frictional forces, it's always valid. But if we have some frictional forces to dissipate energy, gradually the mechanical energy will decrease and decrease and decrease. So the bob will not get the same height when it oscillates. And so in each oscillation, it goes to a lower and lower dead point. And finally, it will stop at the rest point in vertical position. A pendulum bob is released from rest 0.15 meters above its rest position. As you see, the rest position is here, is 15 centimeters above the ground, the maximum height. Ignore frictional forces. If you ignore frictional forces, you can use conservation of mechanical energy. Calculate the speed as it passes through the vertical position. Means that when it's passing through here, we should find the speed, maximum speed actually. What should we do here is very easy. We can use conservation of mechanical energy. At this dead point, we have no kinetic energy, but we have a whole mechanical energy in form of gravitational potential energy, mgh. In rest point, we have zero potential energy, it's in ground state, but maximum speed, a half of mv squared. Again, I emphasize this is called rest point, not because it's at rest, because if there is no mechanical energy for the bob, it will rest here forever. We put them equal. The total mechanical energy here is equal to the total mechanical energy here. We can drop the masses from both sides, and so GH is going to be equal to a half of V squared. So V squared is 2GH. Then we take a square root. And finally, the speed is going to be square root of 2GH. Let's plug in the G, the gravitational acceleration, for 9.8, and the H is given to be 0.15 meters. And finally, the answer will be 1.7 meter per second. The speed of the bob when it passes through the vertical position. A ball of mass 0.35 kilogram is thrown vertically upwards at a speed of 8 meter per second. So let's say the speed here is 8 meter per second. Ignoring frictional forces means that you can use conservation of mechanical energy, calculate the initial kinetic energy. Okay. The maximum gravitational potential energy and the maximum height reached. Okay. Maximum height reached may be this, and when the ball stops at the peak point, okay? At the beginning, if it's supposed to be the ground state, there is no potential energy, but we have kinetic energy. So the mechanical energy is wholly kinetic energy. So kinetic energy at the beginning is a half of mv squared, the initial kinetic energy. Let's plug in the values, the mass 0.35 and the initial speed 8 as mentioned. So the answer is going to be 11.2 joules. This is the total mechanical energy also, because there is no frictional force, and when it's going up and up, basically it's not losing mechanical energy, but just losing kinetic energy. So this kinetic energy may change, but the total mechanical energy, no. This is why the maximum gravitational potential energy when the ball gets the peak point will be again the same, 11.2 joules, because we have no friction and no dissipation, so same mechanical energy. At the top, mechanical energy is just potential energy. So maximum potential energy, gravitational potential energy is 11.2 again. No need to any calculation. The maximum height, okay, it's very easy. We can put the kinetic energy here equal to the potential energy here to find the height. Very easy due to conservation. mgh is the gravitational potential energy at the peak point, is equal to 11.2. Okay, then let's plug in the values, mass, gravitational acceleration, and my goal, h, maximum height. The height is gonna be 3.4 meters, maximum height. In ski jumping, competitors glide down a steep, low friction ramp before taking off. When they say low friction, friction is not ignored. It's small but not ignored. A ski jumper of mass 60 kilograms starts the in-run phase from rest and reaches a takeoff speed of 90 kilometers per hour after traveling a vertical height of 40 meters down the ramp. Okay, let's say the ramp is like this. This ski jumper starts from here, from rest, and then it gets maximum speed here. V is 90 kilometers per hour. And this is a height of h, 40 meters. Calculate the ratio of final kinetic energy divided by initial potential energy. Okay, good. Here you see that potential energy at the beginning is the whole mechanical energy the object has. And finally, the object will get maximum kinetic energy and it has lost its potential energy. And let's say this is the ground state. Okay, let's do it. The kinetic energy is going to be a half of mv squared and the initial potential energy mgh. Regardless of the mass of that, because we can easily simplify the mass, we will have v squared divided by 2gh. Let's plug in the values. Just before I plug in the values, notice that h is in SI units, it's 40 meters, it's good. But v is not given in SI units, 90 kilometers per hour. So let's divide it by 3.4, 90 divided by 3.6, sorry, to convert it to meter per second. It's gonna be 25 meter per second. This is the maximum speed in SI units. Then we can plug in the values. 25 squared divided by 2 times gravitational acceleration 9.8 and 40 meters height. The answer is 0.8. Be notified, 0.8 means that the final kinetic energy is smaller than potential energy, initial potential energy is smaller than 1. So final potential energy, the initial potential energy is larger than final kinetic energy. Means that part of the energy, mechanical energy, was converted to internal energy due to that small friction we have. Part B, calculate the work done on the ski jumper by any resistive forces. Okay, let's suppose that we have a small resistive force all along the motion. So here if I have the total mechanical energy of something, let's say it's E1, and here if I have the total mechanical energy of E2, E2 is necessarily smaller than E1. Actually, this is 80% of that, as we found. So basically, the lost mechanical energy has already been converted to internal energy. And this is exactly the work done by the resistive forces. So if you are going to do that, let's find it in this way. Final mechanical energy, which is in form of kinetic energy here, minus initial potential energy, initial mechanical energy at the beginning. If this difference is 0, there is no frictional force. But if we find something, we have some work done by the resistive forces. Let's do it half of mv squared minus mgh. Use SI units only. So it's gonna be 0.8 mgh. It's very important that previously I found that a half of mv squared is 0.8 times EP. And EP is mgh. So instead of a half of mv squared, we can easily use 80% of the initial. Final is 80% of initial. It's easier. So the answer is going to be negative 0.2 mgh. The negative sign indicates energy loss. The work done by resistive forces must be always negative. Let's plug in the values. The mass of the skier is 60 kilogram, gravitational acceleration, and h, 40 meters. The answer is negative 4.8 kilojoules. The energy, the internal energy actually produced is 4.8 kilojoules because the work done by the frictional forces is the internal energy escaped from the mechanical energy. The in-run ramp is 75-meter long. Okay, so let's say this ramp has a length of 75-meter long. Estimate the magnitude of the average resistive force on the jumper. Okay, we know that resistive forces are always against the motion. So in every point, the resistive force of F is acting on the skier to impede its motion. So here I can say the work done is the magnitude of the work done, is the frictional force times the distance traveled. We can plug in the values. We have already found it, 4.8 kilojoules. This is kilo, 10 to 3, to convert it to SI units. This is my goal, the frictional force, and this is the distance traveled. So it's gonna be 64 Newton. The average frictional force acting on the skier on the ramp. A steel ball of mass m is attached to the end of a weightless string of length r and made to move in a vertical circle, as you see. So it's a vertical circle, the radius is r, the speed of the ball at the lowest point of the circle is u. Yes, it's the minimum height, minimum altitude, and it's the maximum speed necessarily, u. Let's say the ground state of the ball is here. The only forces acting on the ball are the weight and the tension in a string. So there is no frictional force. Good. We can use conservation of mechanical energy. State the work done by the tension in the string during one full rotation. Okay. Guys, you know that tension of the string is always a force perpendicular to the velocity. The reason is that the tension now is part of the centripetal force, and it must be always perpendicular to the velocity because it's along the radius, and the velocity is always tangent to the circle, so they are perpendicular to each other. The work done basically is force times displacement times cosine of the angle between D and F. Okay. Displacement, micro displacement, point by point, is along the velocity. So if we turn on a microscope on the path, point by point, when the object is moving on the circle, it has very small, almost straight line motions. In each small infinitesimal displacement it has, it's moving to the direction of its velocity, and the velocity is perpendicular to the tension force. So this is cosine of 90 degrees, and it's gonna be 0. Tension as a force perpendicular to the displacement and to the velocity in every point cannot do any work. It's always work-less force. So the angle between the tension and the velocity is always 90 degrees, so the work done is 0. Keep in mind that if a force is perpendicular to the velocity, it cannot do any work. We already mentioned it in previous videos. Part B. Derive an expression in terms of u and r. U was the speed at the bottom part, for the speed v of the ball at the highest point of the path. Okay, so here we have the speed of the ball at the top point to be v. The bottom point, we have the speed of u. Okay, let's do it. We know that we can use conservation of mechanical energy because we ignore any frictional forces. So let's say this is the point A and this is the point B. And more than that, let's say the point B has the minimum height the object can get is the ground state. Minimum height. So the gravitational potential energy is gonna be 0 here. The potential energy is 0 at the point B. EA is equal to EB. EA is the mechanical energy at the point A. At the point A, rather than the kinetic energy, because it has a speed, we have also potential energy. because it's at a height relative to the ground state. But at the point B, the energy is just kinetic energy because it's in ground state and no gravitational potential energy. So at the point B, it's just a half of mu squared, but at the point A here, we have kinetic energy, a half of mv squared, and the potential energy, mgh. H is 2r because relative to the ground state is at the height of diameter of this circle, 2r. Okay, here we can drop the masses from both sides. We factor and then drop them, and then multiply both sides by 2. If I multiply it by 2, it's gonna be v squared. I multiply it by 2, it's gonna be 4gr. I multiply this by 2, it's gonna be u squared. That's all. Here we can solve it for v. Let's say v squared is u squared minus 4gr, and then take a square root. Show that the ball will not reach the highest point of the path, I mean the point A, unless u is larger or at least is equal to square root of 5gr. What does it mean? At the point A, there are a couple of forces acting on the object. The downward force of mg and the other is a tension. These two forces are add up to make the centripetal force. This is centripetal force and these are the supporting forces. Look at the right side. The only thing we can change is the speed at the point A. If we reduce the u, accordingly we will reduce the v. So the smaller the v, the smaller the tension, because mg is constant. This tension cannot be less than 0. If this is so, the string will not remain taut, and so it will not get the point A. That's all. Because if the string is not tight stretch, it cannot get the point A. That's all. So the minimum force we can consider, tension force at the point A, is going to be 0. If we take it to be 0, this is the minimum speed here, and accordingly this is the minimum u we are looking for. We are going to show that this u cannot be less than a square root of 5gr, minimum u. Okay. Now let's continue. Here, as we already supposed that we are at the minimum condition for having the taut string and the object will get to point A, f is 0. So mg is equal to mv squared divided by r. Keep in mind that this is the minimum velocity at the point A, minimum possible velocity to get the point A. So if we drop the masses, we will have v minimum square root of rg. Now, again, we can impose the condition of conservation of mechanical energy. This is the mechanical energy at the top point, kinetic energy plus potential energy, EP, at the point A. And here we have mechanical energy, which is the kinetic energy at the point B. Same as the previous one. And then we can write it like that. We have already multiplied both sides by 2. This is the outcome. And then we can drop the masses. Here we have Rg plus 4Rg is equal to u squared, u minimum. So u minimum square is going to be 5Rg. And then we can take a square root and get the result. U minimum is going to be square root of 5Rg. Less than that, the object cannot get the point A because the string is not going to be taut at the point A. Part D. It is given that radius is 1.2 meter. Calculate the minimum value of u so that the ball reaches the highest point of the path. This is just a substitution of values. We use the previous formula. Minimum u is square root of 5Rg. Radius is 1.2 and g is 9.8, gravitational acceleration. So the minimum speed at the bottom point is 7.7 meter per second. A block of mass 6 kilogram is dropped onto a vertical weightless spring. The spring is initially unstretched, so it's in relaxed point. The speed of the block just before it makes contact with the spring is 2 meters per second. The block instantaneously stops when the spring is compressed through a distance of 5.1 centimeters. So the compression of the spring is 5.1 centimeter and it instantaneously stops here. Calculate AI, the initial kinetic energy of the block. Okay, initial kinetic energy is just a half of mv squared. It's very easy. Mass is given to be 0.6 kilogram and the speed 2 meters per second. Just plug in the values and get the result, 1.2 joules. Double I. The work done on the block by the gravitational force since the first contact with the spring until it stops means that through a distance of 5.1 centimeter. Here, you know that gravitational force is always downward, mg downward, and the distance traveled is h, again downward from here to here. So if I'm looking for the work done on the block by the gravitational force, I will ignore any other forces except mg. So mg is downward, displacement is downward, the work done is mg times displacement times cosine of 0. 0 because mg and h are both downward, so they make an angle of 0. Cosine of 0 is 1. So the answer is just mgh. I plug in the values, mass, gravitational acceleration, and this is the displacement in meters. Centimeter is not SI. The answer is going to be 0.29 joules. Part III. The elastic potential energy is stored in the spring at the instant when block is at rest. Here the block is at rest. Immediately you may consider the elastic potential energy of a half of k h squared. H is the displacement, okay, the compression of a spring. Yes, it's a good idea, but do you know the spring constant? It's not given in the question. This is exactly the problem. We can't find it through this approach. What should I do? Here you see, we can ignore the friction. If we can ignore the friction, we can use conservation of mechanical energy to find it. Why? Here at this point, the object has kinetic energy because it has a speed, and also gravitational potential energy. Let's say it's potential energy of gravitational, EPG, okay? Here, the object is at rest, kinetic energy is 0, and if we take it to be the ground state, there is no gravitational potential energy. So the energy is just elastic potential energy, EPE. Okay? So from point A to the point B, EK plus EPG at the beginning will be equal to EPE, elastic potential energy at the end. And we can find the elastic potential energy at the stopping point. Let's find it. Here I have mechanical energy in form of gravitational potential energy and kinetic energy at the beginning, and then just elastic potential energy at the end. Let's put them equal. I'm looking for this one. I have everything on the right side. I know the mass, I know the gravitational acceleration, I know the height, 5.1 centimeter, will be converted to meter, and also the initial speed to be 2 meters per second. Let's plug in the values, and then the answer is 1.5 joules. Hence, calculate the spring constant. Spring constant is K. I know that here the elastic potential energy is 1.5 joules. On the other hand, elastic potential energy is a half of kx squared. X is the compression. So let's plug in the values. Only should remain, again, in SI units, 5.1 times 10 to negative 2. And that's all. Let's do it. Here I have K, my goal, distance or compression in SI units. And finally, K is 1,153 Newton per meter, spring constant. Part C, determine the acceleration of the block at the instant when the block is at rest here. Guys, here the block is at rest, okay? There are, you know that acceleration is obtained out of the Newton's second law. Net force acting on the object is ma. I'm looking for acceleration and I know the mass of the object is here. Just, I'm gonna look for the net force acting on the object at the bottom point. You know that at this point, there are two main forces acting on that. First is the downward force of mg, and the other is the upward force of elastic force, force of a spring, kx. You know the elastic force is spring constant times compression, kx, and it's upward. Okay? These two forces will fight and make an acceleration upward. I know that net force is upward because kx must be larger than mg. Why? Because when here the object stops, again it accelerates upward. Direction of acceleration will be a good guide for finding the direction of net force because net force and acceleration are always to the same direction. So here I write net force equals ma. We have everything except acceleration. Let's do it. Spring constant, compression, and here mass times gravitational acceleration g, and here mass times acceleration. That's all. You can find the acceleration to be 88.3 meter per second square at the bottom point. We are done and I'm really thankful to you because of your attention. Take care. See you.